Cool. So hi, I'm Jacqueline Olis, Chief Product Officer at Saturn Cloud. Today I'll be talking about Docker for data scientists. Um, Before I begin, if you have questions during this presentation, please drop them in the chat or in the Q&A. I guess the Q&A is probably preferable, but whatever, just drop them somewhere. I probably won't answer them till the end because it is very hard to keep a train of thought during a presentation and answer questions, but I will definitely look at them at the end. Cool. So before we begin, disclaimer, I am not a professional engineer. I'm a data scientist. Likely you are as well if you're watching this Docker for data scientist presentation. So everything I've learned has been as a data scientist using Docker in my workflow. But if you're an engineer, a word or two I may say may not technically be exactly correct, but it is directionally correct. And forgive me if I don't get everything exactly right. So just want to preamble. This is more about learning the concepts than learning exactly technically the nuance and what's happening. This is all about just getting started with Docker. So, okay, with that. So I don't know if you've had this as a data scientist, but when I was a data scientist and I was starting out really earlier in my career, I had this problem and it would happen all the time where I'd write some code, I'd make a dashboard, I'd even make an API, I'd do something like that. And I'd be like, man, I wish I could take this code I wrote and put it somewhere that other people can use it. And it turned out that was much harder than I would have expected. If I was making a dashboard or something like that, there wasn't just a put it on the internet button I could press. And that was very frustrating for me, right? Like I'd love to have made a little app in Python or R and then just have it available everywhere on the internet. Now you may say, if you're watching this, oh, I know this cool website that I can upload a Python or R or Julia or whatever app to, and it kind of does, but like there's not like a nice easy general solution to, I just want my code to live somewhere else. This is a thought I've had for much of my career. Spoiler, the thing we're going to be talking about today is Docker, which is going to make that idea much easier. So specifically, consider that you're a data scientist and you've written something. Maybe it's an API, right? You're going to be writing code that will, you trained a machine learning model and you want other people to like be able to make predictions with that model. So maybe you're hosting an API, maybe you're making a dashboard with Dash or Shiny, and you have your dashboard, you made it, it's beautiful, and you just want it to live on the internet that anyone can use it. Or maybe you even have an arbitrary script that runs on a schedule. So you really like once a week, the script to run, but you don't want to have to manually hit run yourself on your laptop. And again, throughout my data science career, I was kind of shocked at not only how many times other people will just be like, well, we'll just say, well, I'll just manually run the script myself once a week. But so many times it ended up being easiest for me to just hit run on a script myself every week, rather than figuring out a way to move it from my laptop to a more general location. And this could be because I want the code to be available publicly so anyone in the whole world can see my dashboard. Maybe I just want an API that's available internally within the company. Maybe I want an API that's available so that when customers are using our product that my company builds can actually use the models I train, things like that. There's a lot of cases where you might want this kind of functionality. But as a data scientist, historically, earlier in my career found this very challenging of a problem to solve. So in essence, this isn't really a talk about Docker, although we'll get to that, and it is a talk about Docker. It's really a talk about making your code run somewhere else. So how can you take code that you've written and have it run in a place besides your laptop? And again, spoiler, Docker is a very good solution for that. So step one is, if you want it to run somewhere else besides your laptop, you probably want your code to run on a server. You may have heard the term server before. Throughout my career, I found the term server intimidating. But in fact, servers are just computers that are running in a centralized location. And I didn't know this for like the first 10 years of my career. I thought servers were like special computers with special operating systems and special programming languages, but they're not. A server is just running Windows or Linux or whatever, just like your laptop is, but it's just running somewhere else. The nice thing about a server is they have a couple benefits. One, in general, they're always on. Two, they generally restart gracefully. So if the power goes out, they know how to turn themselves back on. Another great property of a server is it's managed by someone else. So you don't have to worry about did someone spill coffee on it? You don't have to worry about it. It's living somewhere else. Also, it can have more memory and CPUs, like more power than your laptop usually, because it's just located somewhere else and you have a fixed budget in your home office. And if you have some sort of application, an API, a dashboard that's getting lots and lots of traffic, in theory, servers can do things like you can spin up a bunch of different servers and have traffic routed randomly to the different servers to kind of offset the load. So there are a lot of benefits to servers, but at their core, a server is just a computer running somewhere else. That picture on the right, for a while, I had a viral website I wrote. I had it living for several years just on an old desktop computer in my closet. So like literally you could type in www, like the website I wrote, and it would just connect to my closet desktop that was like 10 years old. That was bonkers to me. And technically that was still a server. I did not previously believe a website could just run on a computer like that. But in practice, when we talk about servers, you're usually talking about a virtual machine. So if you see in those pictures, you have like a server rack, like in a movie or something, you're like, look at all these servers. So a server rack is a big box that has a lot of computers. Each one of those little rows is one computer. But it's kind of annoying if each time you wanted to do something on a computer on a server, you have to take up a whole one of those little boxes inside of it. And the idea of a virtual machine is, rather than having each server be its own like physical box, what if we had one server just actually emulate running a bunch of little tiny servers inside it? So in general, when you are using a server, it's rare that you are actually using the whole server. In practice, what you're doing is you're kind of just using a slice of the single server, which is all stored in a rack of many servers. So using a slice of the single server, which is called a virtual machine. And a virtual machine doesn't actually have to have the same operating system. So you could spin up a Windows server and have a server running Windows, but then within Windows, you can have a little tiny Linux running, a little tiny Red Hat. And the point is, when you're using a server, in most cases, you don't even have to worry about the actual, like, what box is it on? You really just, like, you are just actually using a single virtual machine. So it's not even taking up the whole box. And in practice, you get all the same things you would as if you were using a laptop. It still has an operating system. It still has all of this, but like it's running alongside lots of other virtual machines as well. You may have run virtual machines on your home desktop. Sometimes data scientists have to do that. And it's just the idea of like a little tiny server inside of your server, inside of a rack of many servers, inside of a big building with thousands of these racks. That's fine. But the cool thing is that with today's modern cloud services providers, you can just rent these virtual machines. So you can just rent a slice of a server anytime you want. Now, each of the different like cloud providers gives it a different name. On Google Cloud Platform, they're called VMs. Amazon Web Services, they're called EC2 instances, which you may have heard of a lot. That's, I think, generally the most common one. And Azure VMs also. All of these ideas are just, hey, I'm going to rent a computer somewhere else by the hour. And so if I want my shiny, my R shiny dashboard to run somewhere else, I could just rent a server by the hour and set it up there, or my Python script or whatever. But the point is I can rent some time on someone else's server. So this is the first way you could set up to have your code live somewhere else. So instead of running your code on your laptop, you could run it on a virtual machine on a cloud. So this is version 1 of, hey, how do I get my code to live somewhere else? So 1, you go rent a virtual machine on AWS, GCP, or Azure. So I have the picture on the upper right. You generally set like what operating system does it have? How much memory are you going to be using? How much CPUs are you going to use? You also set who can connect to it. Is it publicly available? Is it not? You then start the server. And then you remotely connect. So from your laptop, you then log into that server. But like once you log in, it just looks like Windows or Linux or whatever, but it's just actually somewhere else. So you're on your laptop, but you're connecting somewhere else. So then if you want to deploy Julia or Python or R, what you would then do is once you've connected to that server, you would install Julia, Python, or R. You'd install your packages, your TensorFlow, your Shiny, your whatever. You'd install your packages on that server, and then you'd hit run on your code. So like on your little remote desktop, you'd hit run, and that would start your app running. And if you set up the connection settings correctly, you could even have, if you have like a dashboard, people could even connect directly to that. And so it took me about 10 years into my data science career before I actually did this for the first time. And this felt like magic to me. The idea that I could pay money to a cloud provider to get a computer to run my code on that anyone in the world can connect to, I don't know. I just found that very astounding. So the pros and cons of setting up a virtual machine to run your code. Well, the pros, you are solving the problem. Your code is no longer running on your laptop where you could turn it off accidentally or spill coffee on it. And now you are paying money to have it run on a different computer. So your code is running somewhere else. You solve the problem. And as I said, this feels like magic. At least it did to the first time to me, of the idea of, hey, I can just have a computer running in the cloud somewhere and doing my stuff. The cons are, though, that I had to manually set up that virtual machine. I had to then install R, install Python, install TensorFlow. I had to set it all up. If I set up something incorrectly, like installed the wrong version of R, then like that could break my installation. Like I could accidentally delete a file on that virtual machine, and then the whole thing would be ruined, you know, if I deleted some very important file. And if the VM was destroyed, if I accidentally turned it off, if I didn't pay my AWS bill, I would then have to do that whole set of steps all over again, right? If I wanted to set up a new server, I'd have to install R, install the packages, get the Linux libraries right, install Python. Even if I had another application I wanted to run, if I had a second application I wanted to run on a second server, I would then have to go through all of these steps again. So the cool thing is wow, I've now been able to rent a computer somewhere else for money that I can do my stuff on. The downside is it's actually just as annoying as having a laptop, but I just have to do everything again on a whole nother machine. Which brings us to version 2 of how to solve this problem, which are virtual machine snapshots. If I'm like, oh, hey, it's cool that I could set up a whole computer on the cloud. That was great. Wouldn't it have been nice if I didn't have to do that setup each time, though? Wouldn't it have been nice if I could take a snapshot of that virtual machine, of just like take a picture of that virtual machine in whatever state it is, you know, after I install R, after I install Python, after I get everything ready, just take a snapshot of that. And then every time I want to set up a virtual machine in the cloud, just start from that snapshot. So in essence, if these virtual machines are just programs running on the actual server, they themselves, you could take a snapshot of it, and then your program becomes data, and then you can store the data, and then you can load up a new virtual machine from data. And you get this weird like Inception kind of thing where programs are data, computers are programs, and like, I don't know, definitions become meaningless as everything falls together. But the point is that just because we are emulating computers, we can take a picture of that computer and use it to set up. And so now I've solved the problem of, 1, I can now run my code on the cloud, and 2, I don't actually have to do the annoying setup anymore, because I can just do the setup once, take a snapshot of it, and then use it for everything. So pros, I don't have to worry about my virtual machine getting destroyed because I've taken snapshots of it. And now I can even duplicate that snapshot every time I want to use it. The cons of this method are, if I take a snapshot of a virtual machine, if I just take a picture of how my virtual machine is set up, well, I don't actually know how I set it up. So it's hard to keep track of like, well, what did I actually install? What versions of things are on there? 2, these snapshots are really big. If they capture everything in the operating system and all the files I've loaded and all the data and all of that on the virtual machine, these files can become enormous, these snapshot files. I can't undo any steps, right? Like if I installed something on that virtual machine and I didn't like it, it'd be kind of a hassle to like spin it up again, uninstall the thing, take a snapshot, like it just gets messy. And if I have a bunch of virtual machines that are nearly the same, like each one is mostly the same, but has like just a couple different files, then I still have to store all of those snapshots, which are all going to be very big, even though they're mostly the same. So this leads us to version 3 of how do I get my code on a server to actually run it, which is, what if I had a way of keeping track of all the steps I had to set up the server? And I had a way of taking a snapshot so that each time I installed a new thing on that server, or I made some change to that server, I could take a snapshot in that moment and be, here's the change. And I could store all these snapshots separately so that if most of my virtual machines are almost the exact same, I didn't have to keep track of, like, I didn't have to store the whole thing because most of the snapshots are the exact same. I just have to store the last few snapshots differently. And what if I had a way of running these snapshots very efficiently? And that brings us to containers. The punchline you've been waiting, oh, I can't see the clock, but probably 15 minutes for. So this is the whole concept of containers. So here's the idea, is that we're going to have something called a Docker image. And a Docker image is going to be a snapshot of a computer that you can run. So an image may be something like, it is a computer that has Ubuntu, the Ubuntu operating system, it has Python installed, it has extra Python packages, and then a dashboard that runs when you start it. So a Docker image is the collection of all those things. And Docker images are built on top of other Docker images. So to build a Docker image, I would start by taking an image that just has Ubuntu. I would add on a layer to that image that adds Python, and I'd add another layer onto that that adds the packages. So these are all layers built on each other. A Docker file is what specifies how I build the image. So the Docker file are all the steps to install the stuff on that image. A container is one of those images that is then running. So if the image is the snapshot, the container is the computer running with the snapshot. So typically when you run a container, you have to use a program to run it. So you can by default use Docker to run the container itself. Or if you want to use the actual production stuff, typically use a different program to run it called Kubernetes, which we'll get to. And so Docker can refer to this whole ecosystem, all these different terms like a Docker image, a Docker file, a container. When people talk about Docker, it can turn this whole ecosystem or literally the program you do to run, the program you use to run these steps. So Docker often has a dual meaning. So for example, here would be one Docker file. So a Docker file is going to, again, specify how we build up these virtual machines somewhere else. So first, I'm going to specify for my Docker file, I'm going to specify what is my Docker file building off of. So it's going to start by building off of an image that just has Ubuntu on it. And it's Ubuntu version 20.04. There are lots of images in the world, some that have just the operating system, some that have like TensorFlow installed already. There's lots of images. In this case, I just take Ubuntu. And then I'm going to use run to say, OK, I'm going to run an apt-get update, and I'm going to install a particular Linux package called wget or wget. I don't know. So I'm going to do that step to install some Linux things. Then I'm going to download and install Python from Anaconda. Then I'm going to install TensorFlow. Then I'm going to set an environment variable of this image. I'm going to copy over my script. And then I'm going to set the entry point. And so the entry point is the thing that says, when this computer turns on, what do I want to have it run? So in this case, this Docker image, when you run it, it's going to run the Python script, myPythonscript.py. So the idea for this particular image is it's going to start with Ubuntu, install Python and the Linux libraries that I need, copy over my Python script, and then run it. So if this is my Docker file, I would build it using the build command. And then I could run it by doing Docker run, which is the command that says, hey, take the image once it's built, and then start it as a container and run it. And so the run command, you specify some things about how you want it cleaned up after, how interactive you want it, if you want any ports open for web traffic for like a dashboard, and then what image you want to run. So that's all cool, but I think this is way more fun and interesting to actually show you live in practice what I'm talking about. So here we go. So I'm going to open up. So I have a little folder here on my computer, and it has two files in this folder. One is an R Shiny application, and I'll actually just pop it open real quick. Let's see. Give me one sec. Give me 1 second. I forgot to open this before. So give me. So here we go. So I'm going to open that file. So we're going to go to the Docker demo, app.r. We're going to wait a second. This is where there's hold music, because I forgot to set up this one part of the demo. If this takes more time than this, I'm just going to ignore this step. OK, forget it. Doesn't even matter. We're going to ignore this step. The point is, this is on our application that's just going to show a very simple dashboard. This is the default dashboard that ships from RStudio. It's just a dashboard in Shiny with R. If you're not an R user and you're like, I don't know anything about R, I'm getting turned off by the fact that this file even ends in a .r. Do not worry. Everything I show you, it is the exact same thing if you were to use Python commands in Python. It's just I'm more comfortable in R, so I just randomly picked R as my demonstration. But the point is, I have this R application, and what I want to do is that's a weird error. These are all fascinating errors. Anyway, I want to host this application somewhere else. So what I've done is I made a Docker file. So my Docker file here for this application is first, I'm going to load up an image that already has R installed. So Rocker is a group of people who make Docker images that have R built in, which is really nice and helpful. So I'm going to start with their particular image. And then I'm going to install a bunch of Linux libraries I need to get Shiny to work. What do all of these Linux libraries do? I don't know. This is just slowly built up over the many years of me using Docker of like, I loosely know these are all things that are helpful to Shiny. I could probably remove some and it'd be fine, but I don't know. I just install them. Then I'm going to run the R script to install the particular R packages I need. Then I'm going to copy that one application file, that app, onto the Docker container. And then my entry point for this container is going to be run the R script, and in particular, run the R command that starts that Shiny server. So that's my Docker file. The way I'm going to build this into a Docker image, I'm going to bundle it up all into one snapshot, is I'm going to do Docker build -t, which is the name I'm going to tag it. So I'm going to call this Docker demo. And then dot, meaning just bundle everything up that's in this particular folder. So I do this. And what you're seeing is, OK, it's starting to build. And so the first thing it's doing is it's downloading that rocker.rver image. And that's a pretty big image, so it's going to take a little bit. So it downloaded that. And then it ran these different commands to, it actually turns out I ran them earlier, so they're already in the cache. So it ran this command to install the Linux libraries. It installed Shiny, it copied that file over, and it set all the image. So my image is now built. So if I do Docker image list, you'll see I actually have an image I made here called Docker demo. So this image is 1.06 gigabytes big. That's all good. So now I can run it. So I'm going to do Docker run. And this .rm just is a cleanup thing. This IT is just an interactive thing. You don't have to super worry about it. What is important is this port thing. So -p says all the traffic that comes to this computer, I want to route to that Docker container. And in particular, any web traffic, which is port 80, I want to route it to this particular container. So I set that port, and then I'm going to set, the image that I want to run. So I'm going to run Docker demo, the image I just built. So when I do that, it says listening, which means the app is online. And so here, if I go to my home file or my home IP address, I now get that Shiny demo, that app.r file. So this may not seem interesting on its face. Be like, oh, cool, you ran an R file from your computer. How neat and interesting. You could have done that without Docker. But the thing that's huge is that I could uninstall R from my computer and this program would run, right? Because this Docker container is running inside of my computer as its own separate ecosystem, it is unrelated to anything else that's on my computer. And importantly, I could take this Docker demo image, I could send it to another computer and use that same Docker run, and it would run. It does not matter what version of R that computer has, if it has R at all. It does not matter if that's a server, a laptop, if that is Mac or Windows. So long as I can send them that image, that code will run, which again, to me is kind of huge because I spent a lot of my career as a data scientist hoping that the person who is running my code has the right version of R or the right version of Python and blah, blah, blah. And like Docker removes all of that because Docker lets you bundle up everything into these images that you can then pass around easily. And when I bundled it up, it used this as my starting image. It added a layer for each one of these steps. And then I set the entry point to start it. So that's the highlight of the demo so far. I'm going to stop demoing, but I'm going to stop for a second and just really highlight that I think this is huge because I think really with just three things, with one, a Docker file, which is just almost standard Linux commands, but with some extra like statements, but basically it's just writing Linux commands. And with two command line statements, Docker build and Docker run, I can take everything I need and bounce it up into a single image I can send to anyone else and run anywhere. And it's just like totally abstracted away the notion of what is this running on? And just this one file can now run anywhere. Again, I think that's huge. I think it's been mind-boggling. It would have boggled my mind if I had known about this like 10 years ago or whatever, earlier in my career. when I was having to deploy stuff and struggling. So that was my initial live demo. So already, I think there's two actually kind of distinct uses for why Docker might be useful. One is for putting code in production, right? If I could take my code, package it up into a Docker image, and then hand it to engineers, they can then deploy it, right? I could have taken that Shiny application, bundled it into an image, sent it to the engineers, and they could have figured out where within my company's network to run the Docker image. So I've now effectively bundled things up. So it's very useful to use Docker for putting stuff into production, or just like actually taking your code and making it more distributed for your whole company. There's another separate use. I don't really use Docker very much for this, but other people do, and like respect for that, is for analysis work, right? If you are doing an analysis as a data scientist and you really want to save it so that 6 months later you can reproduce it, you may have noticed, you may have had a problem as a data scientist where you go to run code from 6 months ago, and now it suddenly turns out it doesn't run because packages have become updated, or you switch laptops and now you don't have the right GPU driver, or blah, blah, blah. You could, again, package up your whole analysis into a Docker container, put the right Linux libraries, put the right versions, things like that, bundle it all into an image. And because an image is a snapshot of a computer, that won't change. So you are guaranteed that when you restart the Docker image as a new container, you will get the same results. So Docker is a nice way to bundle things for analyses. Again, I don't really do that, but I know lots of people do. And again, respect, I just like putting code in production. So, okay, so let's talk about some more concepts that come in with these containers and these images. So one is you may need to debug something, right? So when that container was running, it would be nice if I could not only just see it run, but also could directly enter it. And it turns out there's a way to do this with Docker. So if your container is running an image, you can actually jump right into the image with one particular command. And if your image is built up with a bunch of smaller images, like, you layer on lots of earlier ones, you can always jump into the earlier images too. So I could have jumped directly into that Rocker Arver, or I even could have jumped into some of the intermediate layers that were made while building the final image. I'm actually just going to show this because I think this is a cool thing to live demo. So here's just a very practical example. So if you'll notice in this Shiny app, when it loaded up, here it's loading up and it's running. You'll notice I actually got a warning, which it said, uh-oh, it cannot open shared object file libxt so.6. And like the app seemed to work just fine, but that warning's a little suspicious. So you can imagine, you might be like, I really want to figure out why this Shiny application is giving me this issue. And what you could do is if you Googled it, and this is what I did, if you Google libxt x06, let's see if we get the same. This is really true data science because we're just using Stack Overflow. So if you Google it and you look down for it, you find out that you really need this library libxt st6 installed. So one thing I could do is I could say, you know what, I'm going to close down this Docker container. So I'm going to stop it. I just hit Control-C, and that stopped the container from running. So the whole container shut down. It is no longer running that program. What I can instead do is I can add a -d to mean detached. And so that's going to run this container again, but it's going to run it in the background. So now you can see I'm still on the command line, and you can actually see that this application is still live. It's still running. But now I can actually do other Docker stuff. So I can like do Docker container list, and I can see that that Docker application is running. But I can also do that command I was just talking about. I can do Docker exec IT for like an interactive thing, a Docker exec, and then I'm going to do the name of the image, which is going to be D3A, and then I don't have to write the whole thing, just the start of the name of the image, or sorry, the name of the container, the ID of it. And then I'm going to do the command bin/bash. And now, even though that container is running and doing the actual application, I'm also directly interacting with it. So what I could do is I could do like apt-get update to get the list of all the packages I can install. And then once that's installed, I can install that package that was missing, that I looked for Stack Overflow is missing. So I can try installing it. And if it seems to fix the error, then that's a great sign. And I could say, hey, I know I'm going to always want this as part of the image. So instead, I will put it up here in my Docker file so that I can then rebuild it with the appropriate Linux library installed, and then the Shiny application will work. So the point is, if you want to, like, not only are these computers that like run applications, these Docker containers, but you can also directly enter them while they're running with this Docker exec command. And that gets you like inside of the container interactively, which again is pretty cool. Or, you know, I think it's pretty cool. So where were we? Here we are. So you can directly debug these interactively. You can also store them, right? So my whole point I was saying is, hey, you probably want to be passing these images around to your coworkers, to the engineers, publicly. And when you build an image, it will be on your computer, but it's including all the intermediate images you use to make that final image. But you can send these images to a registry. So Docker Hub is a very popular registry so that it's a public, you know, it's like a public place, kind of like GitHub, where everyone can see everyone else's images. It's like when I installed from Rocker, that R image, that was coming directly from Docker Hub. Your company can also set up its own internal registry on the cloud. So like AWS ECR, GCP Artifact Registry, Azure Container Registry, these are all cloud products where you pay a cloud provider money to store the images for you, which is really valuable because anytime like the engineers want to restart your dashboard, they can just pull the image from the registry and run that. And to push something to a registry is very easy. You just use the command docker push from the command line to take your image and send it to one of these public registries, or to one of the public or private registries. And in general, your images will have a name, like, you know, the owner name / the name of the image, and then you usually give it a version to keep track of, like, you know, generally your images are going to be changing a lot over time. So you give it a different version number to keep track of what version it is. So as I said, you can not just build from images, you can build from any other images. So not only are there images with just the operating system, like Ubuntu, there are also ones with the operating system super slimmed down, because the smaller your images are, the better they work. So they have like tiny OS versions you can use. They also have ones with R and Julia and Python installed. You can also get an image, like you can download an image that has TensorFlow already set up, or TensorFlow already set up to run on a GPU. And by having all these things set up, you as a data scientist don't have to manually set up a computer. You can just use someone else's blueprints to set up a computer for you. This can save you a dramatic amount of time, because, like, you know, you read, like, you're working on someone else's code, you read their repository, and there's like in the README, they're like, here are the 8 steps to set up your programming environment so that this library will run. And you're like, oh my God, this one weird dependency won't install on my computer, and it's very frustrating. Docker extracts all of that, because instead you can just download an image that someone set up for you with all this stuff on it. Like I was saying before, the image size actually does matter. The bigger the images get, the longer everything takes. So if you saw the image I built as part of this demo was like 1 gig, which is like fast enough, but like sometimes they can get to 5 gigs or like 10 gigs. And like at that point, when they're getting really big, it's kind of a problem, because it takes forever to download the images and run the images and things like that. And if you're using someone else's image as one of your starting images, like if you're using the TensorFlow image with TensorFlow already installed, they may have installed other stuff that you don't need, and that makes your image bigger. So in general, when you're building these images, you want to be thoughtful to not add things you don't really need. So like you don't want to add too many extra packages you don't need and things like that, because the smaller you can get them, the better. But there are times where you have to install like a 5 gigabyte GPU driver or something, and that just happens. Also, okay, I didn't necessarily say about this that much, but when you stop a Docker container, right? So you start the container, and then wow, your image is turned into a container. It's running, it's hosting your Shiny app, your Python script, whatever. When that container stops, either because it's like completed running its script or you've turned it off, that container is gone forever. You can never see it again, which can be problematic, right? Because if you imagine, if you have a Docker container with like VS Code in it or something, and you do an analysis in the Docker container, if you just shut off a container, you lose everything in there. That's good for some production cases. Like sometimes that's valuable, but often that can be very bad. So if you want to actually store data as part of your Docker container, like if you want to generate new stuff, you need to do like either have your Docker container connect to an external database, or you can actually mount a drive on your computer or wherever it's running. You can mount a drive to the container. So you can get like more long-term storage connected to a container, but it's not It's not trivial. It doesn't happen automatically. And you have to be thoughtful about it. So if you're doing something where like, it is very important that it saves information, like you just have to be thoughtful of like, what is this container going to do when it shuts off? Is that data going to be saved somewhere? Oh, and here's another wild thing about containers is that the operating systems like kind of doesn't matter anymore, but it kind of does matter. So originally when Docker came out, it really just supported Linux distributions, which means you could have an image that started with any Linux distribution, your Red Hat, your Ubuntu, your Debian, whatever, and it could run on any other Linux distribution. But Windows users are like, hey, we want Docker too. So two things happened. Well, like three things happened. One is that Docker created a program called Docker Desktop. And actually, if you notice what I'm actually doing, you can see I got this little thing here. And this is Docker Desktop. And so if you're on a Windows, I think maybe a Mac, I don't know, I don't use Macs. But on Windows, you actually have to have the Docker Desktop program running for it to run Docker containers. And what Docker Desktop does is it actually sets up all the backend stuff so that a Docker container can run, which is all fine. But if you're a Windows user, you need to have this before you can run images. You can run images that have Linux on them, but you need to have this program. A second thing that happened is Microsoft and Docker spent a lot of money to make Docker Windows images. So not only now can your Docker image have Ubuntu as the starting image, but you can actually have Docker containers that have Windows inside of them. Now, those Docker containers with Windows inside of them can only run on Windows, but that's still pretty cool. And then the other thing that happened is Windows got Linux installed within it with the WSL2 stuff. So you can always just use Linux in Windows to run Docker Linux containers. The point is that largely this stuff all works itself out. If you are using Linux, you can run Linux containers. If you're using Windows, you can use Windows or Linux containers. If you're running Mac, you can run Linux containers. And if you're running Mac, trying to use Windows containers, that's just a weird thing to do. You probably would never want to do that. So the point is that the operating system stuff's a little weird, but it largely works itself out. And then it comes to scaling, which is like, okay, cool. I have that, let's say I have that Shiny app. What if my Shiny app needed 500 gigabytes of RAM to run? Well, what I could do is I could just do Docker run on a computer with 500 gigabytes of RAM, and then I would be fine. So if you need more CPU and RAM, you can take your exact same Docker image and just run it on a bigger machine, and you will get the CPUs and RAM you need. So in some ways, the Docker container is really not limited at all in hardware. You just run it on whatever hardware you need. You may have another situation where your task is fairly not, like it's not something you can parallelize, like a model training, but you really, or like maybe the Shiny app can only handle one person at a time, but you really want to have lots of people using this. So another thing you can do is just run the container many times. So you could spin up a single machine, and on that machine, you could have a container, and you could have many containers instead. So instead of just running that Docker container once, you could run that Docker container concurrently many times and just randomly sort the traffic between them. So not only could you make each Docker container bigger, but because each image is just total snapshot, you can run many Docker containers at the same time, all on one machine. This works. But what happens if that even isn't enough? You're like, well, I would like to have hundreds of machines running in my containers, and I'd like my containers to automatically start and stop. And if lots of people are using a container at once, I would like it to spawn more containers, right? Like, what if I just really wanted this stuff to work itself out at scale? And that leads to the next section, running these containers at scale. So when it comes to running containers, if you just want to run a container on your laptop, you can use Docker, and that's fine. But if you want to run it across many computers at once, you really probably want to use Kubernetes. So Kubernetes is a program that runs Docker containers across lots of computers at scale. So the idea is you have Kubernetes running on your cloud compute environment. So you have like Kubernetes in Azure, or Kubernetes in, Kubernetes in AWS. And what Kubernetes will do is you will give it the container, and it will put it on some machines, and then it will route the traffic appropriately. And then it will notice if, hey, this container is getting a lot of traffic, so I'm going to spin up duplicate ones and pass it around like that. It does like all of this large scale managing for you to really get the value of containers. So these things can automatically start up, scale down. They can balance your traffic. They can deploy new versions of images. So if your image updates, it can automatically roll it out without ever having downtime. You can run containers on a schedule. So if, again, you want to run a container once a week, Kubernetes can do a job that automatically runs that, and lots more stuff. So Kubernetes is really cool. And when people talk about containers, in practice, they usually mean like, they say Docker containers as the way to build them. But usually when you talk about deploying containers, you usually are talking about Kubernetes. But here's the problem when it comes to Kubernetes. And maybe you have had this problem too, if you heard about Kubernetes before, which is Kubernetes seems wildly confusing to me as a data scientist. Like, I understand the concept of like, hey, taking these images and passing them around and having them all managed for you is really helpful. But what if I wanted to deploy my own Kubernetes cluster, right? Like, I can do Docker run to run an image, but like, how do I install Kubernetes? Like, how do I install it in the cloud? I have not figured out how to do this yet. This is outside my pay grade as a data scientist. We are now in the realm of data engineering and stuff, or like DevOps. And I'm like, that is no longer my job. I don't really want to do that. So installing my own Kubernetes cluster in the cloud, not my thing. But good news, many of the cloud providers have these steps automatically set up for you. So you just go to the cloud provider, hit, I want my own Kubernetes cluster. You start up for me, and then I'll use that. An example is Amazon's EKS, Elastic Kubernetes Service. The idea is you just press the button and they already have Kubernetes set up for you. This is still too out of my pay grade. I find this incredibly challenging to use. And I don't know if you're watching this, if you happen to have tried installing EKS before, maybe you found it confusing too. So that still doesn't work. But another option you can use for getting your stuff at scale is you can use a cloud service provider that entirely abstracts away the idea of Kubernetes. And the idea of being, you just hand them the Docker container and they literally figure out everything else. So an example of that is Cloud Run on Google Cloud Platform, which is really cool. And I'm going to do a real quick demo of that. Or you can use some data science tools, which again, entirely abstract away the idea of Kubernetes. So like Saturn Cloud, the company I work for, we are technically on the back end, we are running a Kubernetes cluster, but we abstract all of it away for you so you don't have to worry about any of the Kubernetes stuff. So let's talk about Google Cloud Platform. So the idea of Google Cloud Platform is you tell it how much memory you need and like what's the maximum number of these images you want running concurrently. And then you give it that, and then you get an endpoint to hit your API. And so then it starts your container anytime someone hits your endpoint, which is really good if you have like just a dashboard or something. It's not good if you have like a long running task or whatever, but if you have just like a dashboard, it can work pretty well. So here's how it works. I'm just going to show a demo because this, again, blows my mind at how relatively easy this is. So the idea is that when you go to, so Google's a little fussy and they say, hey, if you want to use one of your Docker images in our Google Cloud Run, you got to put it on Google first. You got to put it in one of our registries. So what I'm going to do is I'm first going to, let me start up a new thing. I'm going to first do this Docker tag. This Docker tag command is just basically adding an extra name to my Docker demo. So I'm going to add the name to the Docker demo of US Central 1 Docker.pcv, blah, blah, blah. This basic string, which is telling Google where to save it. So I've tagged my image, and then I'm going to do Docker push to push it to their registry. And so what this is doing is it's taking the Docker image that I've built on my computer, and it is sending it up to the Google Cloud Registry. Oh, and apparently it was already there because I practiced this earlier. So this is very fast. Normally it takes like 2 or 3 minutes to send a gigabyte of data up, but Google Cloud noticed I already had the image up, so it went faster. So if I go to my Google Cloud, if I actually look, you can see on the Google Cloud artifact registry, you can actually see here's my Docker demo. So here's my image. I sent it up to the registry. And then I can go to Google Cloud Run. I'm going to create a service. I am going to deploy I'm going to deploy the image that I've saved here. So this is that URL I tagged it as, that US Central 1 Docker dev, blah, 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 blah. This is that Docker image I've loaded. So that's this image right here. I'm going to call it Docker demo. I'm going to say I want to have 100 users using this concurrently. I'm going to allow all traffic. And then one special thing I have to do is because I know my container is listening on port 80, I am going to set the container port to be 80, which means that when Google transfers the traffic to my container, I want to transfer it to port 80. Google actually lightly complains about this and it says you shouldn't do it, but I don't care. I'm going to do it anyway. So I hit create, oops, and I will allow unauthenticated invocations, which means anyone can connect to this. So I hit create, and then in just a minute or so, we are going to have a live Docker container, and my Docker container that I built on my computer is running on the cloud. Again, this solves the problem I had when I was a junior data scientist of like, man, I wish I could just have my code not run on my computer and instead very easily run somewhere else. This is solving that. And let's see it. Oh no, maybe that's not the right link. Oh no, that's the image URL. Okay, so it's still building. Oh, I was very excited. Let's see. Here's the URL. Perfect. So here is now my Shiny app. And the thing about the Shiny app is it's single threaded. So if we were running it from my computer, if everyone tried to hit it at once, it would crash. And yet I'm going to put this in the Slack chat just for kicks. In theory, you could all hit that link at the same time and my app would be able to handle it because I told Google to have up to 100 concurrent separate applications running at once. So I don't know if there'll be some sort of like logs or details, but in theory, I should be able to notice that everyone's now hitting this. And in theory, you all should be able to hit this at the same time. And really, this is like 10 seconds of, yeah, I don't know, somewhere in the logs, it'll show lots of people are probably hitting this. Oh, wait, I sent this in the wrong link. Here we go. There, now you all should be able to hit this. Metrics, no, we probably want metrics. This feels like a metrics thing. So in theory, I should be able to, I don't know how quickly this updates, but in theory, everyone should be able to hit this at once. And again, this is code I wrote that's now running at scale in a Docker container, and that should be pretty cool. I think that's quite cool. People in the chat are saying it works. I find this very thrilling, especially having had problems in my career with managing scale and like having these things not work because it all crashes when too many people use it at once. So lastly, let me talk about Saturn Cloud. So Saturn Cloud, the basic idea of Saturn Cloud is we are a cloud platform for data scientists to do their work. And really, we want to do lots of interactive stuff plus deploying. So in many situations, you may want to like run, Jupyter Lab or use our studio and like do an analysis. So like here's like a, here's Saturn Cloud. I can spin up an R Studio server, and then in seconds, I can be editing our studio code. So there's some R Studio code. So on the back end, when you create a resource in Saturn Cloud, on the back end, what we actually are doing is we're using Kubernetes and Docker containers. So every time you start something in Saturn Cloud, you are actually selecting a Docker container to use as the starting image. So what's nice about this, though, is unlike if you're using Kubernetes and Docker and setting all that stuff up yourself, you don't just run the image. We also manage a lot of stuff on top of that. So like, for instance, you would have a base image of like Saturn, which just has Python installed, and then you can install TensorFlow, or you could install whatever package is on top of it. And then those will run at startup. So instead of having to like rebuild an image and push that image to a registry and blah, 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 you get the benefits of using Docker and the scale of using Kubernetes, but like you really don't have to think about Docker at all. You just think about, hey, I want to start up Python. I know this image has Python installed. I'm going to install the extra packages I want right here, and then create it and give it a name. And then create it, and then boom, I'm in Jupyter Lab or RStudio or deploying code. So this is like all the benefits of Kubernetes and Docker without the hassle of having to actually do all that building image stuff and deploying. And like if you want to deploy a Shiny app, I could have also done a deployment here, which is kind of the same thing. I can set concurrent, how many concurrent instances are running, and it could run the Shiny app that way. And again, it is actually running Kubernetes and Docker on the back end, but I don't have to think about it. So I bring this up, especially if you're doing a lot of analysis work. Like I really think for analysis work, it does take a lot of time to do the Docker stuff yourself. So Saturn Cloud is a really nice way to just analyze data, run code, deploy stuff, and not have to worry about this stuff for your whole life. So Saturn Cloud, pretty cool. I like it. I work there. Y'all should check it out. That concludes my pitch. Oh yeah, and you can use our pre-made images in Saturn Cloud, or if you have your own Docker container you built on your own computer, you can upload that to Saturn Cloud too. That's just fine. Okay, so the takeaways from this presentation. One, the important thing are Docker images are just snapshots of running programs you want to run. So they capture the state of a machine, you tell it what program to run when it starts, and you just build it by using the Docker build command. The Docker file is what gives you the blueprints for those images. So the Docker file is what does all the work. It lists all the steps to build the image. And that's like what Docker goes through when you want to build one. A container is one of those images that are running. So when you have a built image, you then turn it, you take one of these snapshotty things and then you say, okay, run it. And that is now a container. Containers can run on your laptop. They can run on the cloud. They can run in lots of different places with different hardware. And then if you want to manage a lot of these, Kubernetes and other tools exist to like do all sorts of scaling and, you know, shifting around and auto restarts and stuff. They're kind of a hassle to manage yourself, I would say, as a data scientist. So you could use a product like Google's Cloud Run or Saturn Cloud if you want to use Docker containers, but you don't want the hassle of managing your own Kubernetes cluster. So with that, oh, the formatting got messed up. But here we go. Okay, the formatting's back. Before I open a question, just 2 notes. One is that later in June, I'm having a demo. If you like R and you like Shiny, but you wish your Shiny apps looked better, I'm having a demo of how you can take a boring looking app and make it into a super pretty one with CSS and Bootstrap and icons. And that's going to be interactive. So we're all going to follow along and do it together. So if you have an interest in Shiny and making Shiny apps prettier, I highly recommend you go to this. You go to scld.io, that's saturncloud.io, but short. Workshops /Shiny to get there. We also have other webinars coming up. We have an introduction to Julia, if you've been curious about Julia, but you haven't taken the leap before. And we have just a more general getting started with Saturn Cloud. If you are at all enticed by the idea of having a cloud provider that you can do all your data science on very easily,